He will be giving talk entitled on Diophantine pairs. Please, Professor Alain Togbe.
Okay, thank you so much. Okay, thank you so much for inviting me. I would like to thank particularly the main organizers, that Kolian and Adizul. I will enjoy coming to your city, your university, but unfortunately, it is the Thanksgiving here, and my family welcoming our friend and nephews, so we will be a lot here starting tonight. So unfortunately, I cannot come in person, but I will try to give my talk and discuss about something that I have done recently. So my talk it is about Diophantine pairs. And here is the outline of my talk. I will give the motivation about the result that I will discuss about. So I will state the main result and give us some idea about the proof. And then I will make a quick conclusion related to the main result. In fact, it will be a good idea to define what is a Diophantine M-tuple. When we have a set of numbers A1, A2 until AM of positive integers, and we look at them and we take the product of two distant or two of them, and we add the number one, for example, and we look if it is a perfect square. Another way to see that it is you can have instead of having one, we can add a number n. So we call that a Dn M tuples. So it's such a set. And these sets, this type of a set, studied at the beginning by Diophantus. And what he did, he looked at some, instead of having integers, he looked some rational. Here is the picture for that. And we can see the book that he wrote, and we can see the study of this type of sets in the book. In fact, he looked a set of 4 rational numbers. And if we take the product of 2 of them and we add the number 1, we can see that it is a perfect square. So here is a list of such a property. So you see, like if we take 1/16 and we multiply by 33/16, we add 1, it gives us 17/16 squared, and so on. But the 5th element was given by Euler, and we can have a quintuple. The main problem is how large this set can be. So, or instead of 1, can we add a big number? And there are so many problems related to the type of a set. In fact, the first quadruple was given by Fermat. And we can see here that if we take the product of 2 of them, we add 1, we have a perfect square. And usually we call these sets Fermat sets. The problem is, can we add a 5th number? So here is the picture for Fermat that we can see online. So So we will come back to the Fermat set. Another example that we can see it is an example given by Gibbs, where instead of having one, we can ask a big number like here. For example, if we look here, we take 99 times 315, and we add the number here, we have a perfect square, 1737. Okay, and so on. Okay. Now, let's talk in general about this type of a set. Let's prove that if we take a Diophantine pair, AB, we can add a third element that is the element A plus B plus 2 square root of AB plus 1. And this following the idea of Euler, in 1979, Akin and Hogarth and Strauss, they showed that we can add a fourth number, that is the number here. Please put in mind that I will come back to the number here. In fact, later we are going to call this number, the fourth number, D plus. Okay. Now, in general, so it is exactly here. We can call that D plus. In fact, what about R, S, and T? R, S, and T are defined here. Like we take a B plus 1, it is a perfect square. That is, we call that R squared. A plus A C plus 1, it is S squared, and the BC plus 1, it is T squared. So this will give us exactly what we have seen before. Let me go back to that, the number we have here. Okay, so that is the D plus. And this can help us to have a conjecture, and in fact, a very strong conjecture. And I will give you the conjecture in a few minutes. In fact, this set, it is called a regular Diophantine quadruple. So here is the conjecture. So the conjecture says that any quadruple, any Diophantine quadruple is regular. It is still open. There are some attempts to prove the conjecture. Like a few years ago, Chipu, Fujita, and Miyazaki, they improve, they obtain some bond. Even they put down the bond to 8. So, but it is still open. So if anyone who would like to attack the problem, they are welcome. But it is a harder problem. Now, because of the type of many things that we have related to that, we organize some conferences. Like here, we organize the first conference related to the problems. And it was organized, if my memory is good, in 2014. And the second conference we organized was still in my university in 2018. And this year, we organized a last one, but this time in Zagreb. And I was very happy to be in Zagreb because from there, we have seen the progress that the progress made, and the new problem related to Diophantine set. So it was a very nice conference in September. By the way, after the first conference, Ziegler and myself, we attacked what we call a folklore conjecture, that there doesn't exist any D1 Diophantine quintuple. So this means that if you take any D1 set, Diophantine set, you will have a quadruple, but not any quintuple. So we proved the conjecture in 2019, but in fact, we proved that before then, but it took us a while to publish that. So after the proof of the conjecture, the problem is, can we do that for other numbers? Instead of one, can we do that for other numbers? So for D4, it was obtained by Filipin and his student the same year, because after we announced the proof of our conjecture, the proof of our theorem, Filipin, we shared that with many friends, and Filipin and his student, they attack the problem for D4. And just recently, for D-1, it was solved by Machua and Chipu and Miot. And they, in the same paper, they attack also the conjecture for D-4. So far, we can see that, oh, by the way, for D-4 and D-1, we don't have a quintuple, but we have a quadruple. The problem it is about a quadruple. In fact, I have a paper where we started with a Diophantine pair. We extended to a Diophantine triple, but to have a Diophantine D-1 quadruple, we cannot have that, but we can extend, adding a number such that it will be a D+1. So that is, so this means that to have a Diophantine quadruple, it is not possible for D-1. Anyway, so those conjectures are solved, but there are still many conjectures related to Diophantine. So there is a nice website created by Dujela, and you can visit that via the website, and you can see so many papers related to Diophantine M2. I don't know how he's able to collect all these results, and it is a wonderful website that anyone looking for some opportunity to solve some problems on Diophantine M2, we need to visit. Okay, what about Diophantine pairs? So a few years ago, Fujita and Filipin, we tried to work on some Diophantine pairs. But to refresh your memory, let's see some results obtained in that direction. So we have seen a few minutes that if we have a Diophantine pair, we can, with Euler, we can extend to a Diophantine triple and then a Diophantine quadruple. For example, Fujita started studying the pair of the form K-1, K+1. So he had some twice. He had a result. Then his result was extended by Bugeaud, Mignot, and Dujela. Another pair that we can see it is the K, 4K plus minus 4. And for K, a positive integer, we started studying that with Filipin and Fujita in 2014. And then we extended that, we extended the result with a heap and chain. Another very interesting pair, it is, we started, in fact, with the pair K, A squared, K, plus 2 epsilon A. So starting with the pair, we first started with the pair in, in 2009. Then we have a result, and we extended the result in 2012, and then Chipu-Fujita and Mignot's obtained a better result where epsilon, in this case, it is plus minus 2, plus minus 1. So maybe someone can look also plus minus 4. Okay. So let's come back to, in general, another definition of a D. I discussed about a D plus. Now we talk about a D minus, where the change will be, instead of having plus, we have a minus here. And we use that to study some pairs. And let me discuss about that quickly. In fact, in 2014, with Filipin-Fujita, we proved that if we start with a Diophantine triple with A less than B, and we suppose that we have a quadruple, okay, with a D greater than D plus, then in this case, we cannot have another Diophantine quadruple for C prime with a C prime between 0 and D minus. And if we have that, we can find the bond for the element C. And with the conditions, we have the bond for C. One thing interesting, it is the third case, the second case. That is what we are going to use in the pair that we will study, and I will discuss about that in a few minutes. So very important is when B is between 2A and 8A, C is less than 9.5 B4. And our result was a little extended by Chipu-Fujita and then by Chipu-Filipin and I'm sorry, here it should be Fujita. Okay. Now, I will pass that quickly. Now, in our main results, we define C nu tau by this expression here. And in fact, if we start with a pair AB with the condition B between A and 8A, we can have R defined by AB plus 1, the square of R, it is AB plus 1. So I discussed about that a few minutes ago. And we define a C nu tau by this expression with a nu from 1 to infinity and tau equal to plus minus 1, in fact. So one thing that we have seen is if we consider a quadruple now, and we want to extend that, we need to have our D greater than C nu plus 1 tau. And if we have another quadruple with a C prime and C, then in this case, the C prime must be less than that. And for this condition, if we have a B less than 2A, then the C is less or equal to C3 plus. And if we have a B between 2A and 8A, then C is less or equal to C2 plus. This will help us to study some particular cases. In fact, the work was done in 2 papers. The first paper was about the general idea of the general ideas on the subject. And the second part, it is to give us some examples. So here are some examples that we have studied in the second paper. We consider the pair k squared minus 1, k squared plus 2k with k greater or equal to 2. We consider also another pair here with the same condition for k. And a third pair we consider here and a fourth one with the condition k greater or equal to 1. And we prove that these pairs can be extended to an irregular Diophantine quadruple. Another way, if we extend that, we cannot have a regular Diophantine quadruple. In the same paper of examples, we studied also a pair of Fibonacci numbers. And the first idea was studied by, in fact, Dugela, and we extended his work, and we proved that the fourth element should be a D plus. Now, for the last example, we have the case B between 2A and 8A, and A it is the 2K Fibonacci number, and the B is the 2K plus 1 Fibonacci number. And in our study, like we have seen, the only possibility is to have a C less or equal to C plus, but in fact, we can have only C1 minus, C1 plus, C2 minus, and C2 plus. And in this case, we can see that C1 negative 1, it is a Fibonacci number. C1 plus, it is not really a Fibonacci number, but it is a multiple of a Fibonacci number, and so on for the other. And we can see here that we have Lucas numbers. In fact, they are both related. Okay, so as I said, the first case was studied by Dugela when he studied C1 minus in 1999. So what happened is we miss in our paper some cases that we didn't study all cases, and Park and Lee in 2019, they consider C in the set C1 plus, C2 minus, C2 plus, and they prove that in this case, to have a quadruple, we need to have D plus. Another thing that we have done in the example is that we look the case we have a K, the pair K, 2K, 4K plus 4 epsilon, epsilon equal to plus minus 1. And we prove that if we want to have a quadruple of this case, then we need to have D equal to C nu plus 1 tau. But our paper was not complete because we found some particular cases, but our paper was not complete, and the video was extended by other authors. So I will pass that quickly to save time. Like he, Boker, Pu, Chen, and myself, we extended the work where we consider the third element equal to C2 plus, and we prove that the fourth element it is exactly C3 plus. That is the maximum that we can have. Now, let's come back to the pair K minus 1, K plus 1 studied by Fujita, then Bijou, Dujela, and Mignot. And if we consider the pair here, we can see that the third element, it is to have a regular triple, the third element, it is the 4K. So will help us to see that it is possible to have a regular one if we consider the pair. Okay, now I will come back to the Diophantine pairs, particularly if we look at V here. If we take a K, I'm sorry, yes. If we look here, we take a K equal to 2. K equal to 2, we have the pair 1, 3. So the idea is to look at the general form because the pair was studied, and we try to see if we can extend or the idea of studying the pair 1, 3, and have a more general pair that is the A, 3A. So, of course, the third element we can add can be defined by C naught tau. Tau, which is the plus minus 1. And the first result is that we can prove that if we consider V the triple, we cannot extend to an irregular Diophantine. We cannot extend to an irregular Diophantine quadruple. The result was obtained by my student Adeji, Boher, and Akos Pinti. So here is the idea. We start with, just to remind you that usually if we have a Diophantine pair AB, we can extend it to a Diophantine, a regular Diophantine quadruple with the idea of Euler and so on. And we can define R, S, and T. In fact, if we take now B equal to 3A, because it is the idea, this gives us a pair equation. And using the idea that the pair equation is related to the quadratic number Q of square root of 3, we can study using the theory of Diophantine of pair equation, we can find the fundamental solution that is 2 plus the square root of 3. So this means that any solution of the pair equation here can be written into the form RK plus AK square root of 3. That will be equal to a power of the fundamental solution for K greater or equal to 0. So the idea of using the fundamental solution, we can define two sequences related to the last expression, because when you expand that, you can define two sequences The first related to AK, and the second related to RK. And we can see that the sequence is defined like that. And using some properties related to sequences, we can, in general, define AK into the form 1/2 square root of 3, and we take the fundamental solutions that that we obtain to obtain the expression of AK and RK. Okay, so having that, we can prove that if we have any Diophantine quadruple that contains the pair AB or A3A, then with A equal to AK, then the Diophantine quadruple is regular. So from the main theorem, we have a corollary, a consequence that in fact the Diophantine quadruple is regular. So how we do that? So we start with, we consider a Diophantine triple with A, B equal to 3A, and we consider also A equal to AK, defined a few minutes ago. We can add a fourth element to the triple, and using the definition of a Diophantine quadruple, we can say that AD plus 1 is S squared, BD plus 1 equal to Y squared, and CD plus 1 equal to Z squared, where S, Y, Z are positive integers. So if we try to eliminate the fourth element D, we can have these Pelian equations, and then using the theory also, we can obtain the sequences related to these pairs, these Pelian equations. So we have all that. The idea is to use the sequences and to solve the problem, and I will give an idea about the way we use the sequences in a few minutes. In fact, using the equation that we have here, we can define the sequences Vm and Wn by this form. There is a theory well developed by Dugela that we use here. And the problem to solve the problem of a Diophantine quadruple comes back to solving this equation here using the sequences defined above. So if we consider two pairs of the previous pair equations, like A y squared minus BS squared equal to A minus B, and AZ squared minus C S squared equal to A minus C, then we come to this equation here according to the sequences that I said, and the PL are defined by this way using the theory of sequences, and the problem is to solve this equation, and if we determine X, then we can solve completely the problem. So the method that we use, it is the Baker's method. Baker's method, for that we are going to consider two types of possibilities because of the initial values of the sequences. So according to, we are going to consider first the type 1, means that if L is congruent to M modulo congruent to 0 mod 2. Another way L and M are even. Then we are going to consider the initial condition Z0 equal to plus minus 1, X0 equal to Y2 equal to 1, and X2 equal to 1. In the case that they are odd, we are going to consider Z0 or 1, it is odd. Yeah, they don't have the same parity. We are going to consider the initial condition here. So for each type, we are going to use the Baker's method to solve the problem. So Baker's method, we know that it concerns linear form in logarithm. So if we take C equal to C1 minus, we are going to consider this linear form in logarithm. And the technique is you use the properties of the linear form in logarithm to obtain an upper bound of the linear form in logarithm. And then we have in the literature some results that we use to obtain the lower bound. And then you combine the lower bound and the upper bound and to have a contradiction. So what we do is we consider first the linear form in logarithm. And if we consider C in C1 plus C2 plus minus, then we consider the second linear form in logarithm, where the gamma 2 here, it is the expression here. For the first case of the gamma 1, it is the expression. Okay, so for the case of C1 plus minus, we obtain this lemma. So we prove that the equation that we have at the end has a solution Lm only when k is less or equal to 34. And in the same time, we have m less or equal to 2, 10 exponent 19. That is a very high bound that we cannot use a computer to solve. In the case, we have the triple A, 3A, C, with a C equal to 1 plus. Then the equation has a solution if we have a K less or equal to 34 and L equal to 2, 10 exponent 19. So we have a similar result. Now, if we consider C plus, we have done the same study and we find the bounds for K and L. So the bounds are a little different here, but still the bound of L, it is very high, and any computer, for instance, cannot handle that. So this means that having the bound a little high, we have to use the reduction method of Baker-Davenport. So that is what we have done, and we prove the theorem. Here is the question. Oh, in fact, this solves completely the problem for D1. In fact, before I will discuss about, yes, let me continue with that, and I will come to the case of D4. In fact, we extended in our main result the pair 1, 3 to any pair A, 3A. So the question is, instead of having 1, 3, if we have 1k squared minus 1, what can be done? In fact, we try that to generalize we form 1n. And when we did that, we obtain this time the pair equation r squared minus na squared equal to 1, instead of having r squared minus 3a squared equal to 1. So we are in the quadratic form q square root of n. So what can be done? We look at one of the results. I said we come back to that, where we have b between 2a and 8a, and we come to the conclusion that in this case, we only have the possibility n equal to 3 and 8. If we want to stay, we want to have our C in the pair C1 plus minus and C2 plus minus. So this means that the second result we may have is the following one. If we start with a triple, A, 8A, C nu plus minus, with a nu in the set of natural numbers, then the triple cannot be extended to an irregular Diophantine quadruple. Another way we can obtain a regular Diophantine quadruple with a C nu plus minus like we have done. So if we stay in the band A2A, a B between 2A and 8A, the only possibility we have it is that. So this was done. We consider the pair AB with a D equal to 1. What about the other values of a D? We try for D4, and recently myself, my student Adeji, and Filipin and his student, we consider the pair AB when D equal to 4. But the paper is under review. So for instance, I won't give the answer. Now, when we were preparing the conference, the third conference on Diophantine M2 Professor Machua sent me a conjecture, and I would like to discuss about that, but I have no idea how we can solve that. So he sent me an email. He said, in the usual definition, let n be a fixed non-zero integer, and let a1 until am be m fixed distant positive integer. If we take ai and aj and two elements, we multiply them and we add n, it is a square. So then A is called what we know, a Diophantine M2 with the property Dn over positive integers. So he denoted by n of mn the number of such sets. So he conjectures that mn is equal to 0 or mn is infinite. Okay, so that is and he asks if this conjecture is true. I have no idea, but can we find any counter example for the conjecture? So I open that to anyone. So you have the conjecture you can think about. And if you have any idea, anything, you can send me an email I will be free. I will be happy to put, or you can contact him directly, because if you look at his papers, you can have his email and you can contact him. But I will stop here. Thank you so much.
Any question from the audience? The room, online?